Across nature we encounter countless speeds. The speed of sound traveling through air, the speed of chemical reactions, the speed at which planets orbit their stars. Every physical system has its own characteristic pace. But among all these motions, there is one speed that stands apart, a number so fundamental that it shapes the structure of reality itself. 299,792,458 meters per second. The speed of light in a vacuum. This value is not simply how fast photons move. It is far deeper than that. It is the maximum speed at which information, causality, and physical influence can propagate through the universe. It is woven into the geometry of spacetime, the equations of electromagnetism, the behavior of particles, and even the flow of time itself. Unlike other speeds, it is not dependent on material properties, temperature, or environment. It is universal, the same for every observer, in every direction, at every moment. This is why the speed of light is not a technological barrier, but a boundary of existence. No matter how powerful a rocket we build or how advanced our physics becomes, this limit is not a wall we can break. It is a law built into the fabric of reality. As the poet of physics might say, this is not the limit of machines, it is the limit of the universe. In this video, we will explore why all roads in physics lead to this one extraordinary number. We will uncover how space and time merge into a single structure, why massive particles can never reach the speed of light, how approaching this limit bends time, contracts lengths, and reshapes the world, and why the speed of light is ultimately the guardian of causality, the rule that ensures effects do not precede their causes. This is not just a story about photons. It is the story of why reality behaves the way it does, and why nothing, absolutely nothing, can outrun the speed that defines the very structure of the universe. When people hear the phrase the speed of light, they often imagine tiny particles racing through empty space. But the true meaning of this speed is far more profound. Light is not simply a beam of photons rushing from one point to another. It is an electromagnetic wave, a self-sustaining vibration of electric and magnetic fields. And the speed at which those fields propagate is determined not by the nature of light itself, but by the properties of the vacuum. In the 19th century, James Clerk Maxwell wrote down a set of equations describing electricity and magnetism. When combined, those equations revealed something astonishing. Electric fields and magnetic fields can sustain one another, forming waves that travel at a specific speed. And when Maxwell calculated this speed, he discovered a number that matched the speed of light. It was then that he realized, light is an electromagnetic wave. But the deeper revelation is this. The speed of that wave is determined entirely by two constants of empty space: the permittivity of the vacuum and the permeability of the vacuum. These constants describe how space responds to electric and magnetic fields. Their values fix the speed of electromagnetic propagation through the equation C equals 1r square root. This means that the speed of light is not about photons being fast. It is about space itself. Even if photons did not exist, even if no star ever emitted a single particle of light, the number c would still be built into the structure of the universe. It is not a speed chosen by light, it is a speed chosen by the geometry of the vacuum. This is why physicists say c is not the speed of light, it is the speed limit of reality. It is the maximum rate at which information, energy, cause, or physical influence can travel. It is the slope of the light cone in spacetime diagrams. It is the measure that separates what can affect us from what can never reach us. Particles that have mass are bound below this speed. Particles without mass, like photons and gravitational waves, are bound to this speed. Nothing can move faster than c because faster-than-light motion would violate the structure of spacetime itself. The laws of physics are woven using this number as their fundamental thread. Thus, the speed of light is not a technological hurdle to be overcome. It is a geometric constant, a foundational aspect of the universe. It is the rate at which reality updates itself, the tempo of causality. In a sense, c is not a speed at all, but the deepest rhythm of existence. One of the most famous statements in physics is that nothing with mass can reach the speed of light. But this isn't just a rule written into textbooks. It is a profound consequence of how energy, mass, and spacetime intertwine. To understand why massive particles cannot attain light speed, we must follow the logic of Einstein's relativity all the way down to its deepest implications. A particle with mass always obeys the relativistic energy equation, E equals mc squared. Here, m is the particle's rest mass, c is the speed of light, and gamma, the Lorentz gamma factor, controls how energy behaves as velocity increases. This gamma factor is defined as gamma equals 1r square root 1v squared c squared. At low speeds, gamma is very close to 1, which means classical mechanics works well. But as the particle's velocity v approaches the speed of light c, the denominator becomes smaller and smaller. When v gets extremely close to c, the denominator approaches 0, and gamma skyrockets toward infinity. This single mathematical fact carries enormous physical meaning. As gamma increases, the particle's relativistic energy increases as well. Not linearly, but explosively. To accelerate a massive particle from 90% to 95% of the speed of light requires far more energy than from 0% to 90%. Pushing it from 99% to 99.9% requires orders of magnitude more energy. And to reach 100%, exactly c, gamma would have to become infinite. That means the required energy would also be infinite. Since no physical process can supply infinite energy, no massive particle can ever be accelerated to light speed. This is not a technological limitation, it is a structural boundary of the universe. Another way to see this is through relativistic mass, a concept that describes how a particle's resistance to acceleration increases as it moves faster. As gamma grows, the particle behaves as if its mass is getting larger and larger. Near the speed of light, this effective mass becomes enormous, making the particle harder and harder to accelerate. Ultimately, acceleration becomes impossible, because the cost of pushing the particle increases without limit. In other words, the faster a particle moves, the heavier it becomes in terms of inertia. The heavier it becomes, the harder it is to accelerate. Near the speed of light, its inertia becomes infinite. At c, acceleration would require infinite force and infinite energy. No object with mass can cross that threshold. This impossibility is not merely mathematical, it is geometric. In the language of spacetime, massive particles follow time-like paths, while light follows null paths. These families of paths belong to different categories of motion, and no amount of energy can rotate a time-like trajectory into a null one. It would be like trying to tilt a vector into a completely different mathematical class. If you could ride alongside a particle as it approaches the speed of light, the world around you would begin to distort, distances in front of you would compress, the universe would contract in the direction of motion, and the sky would warp into a tunnel of blue-shifted starlight. This visual distortion is not just an illusion, it is a direct consequence of space and time stretching and squeezing as velocity increases. The closer you get to c, the more dramatic the distortions become. But the barrier itself remains absolute. Light speed is not simply fast. It is the boundary between different kinds of existence, between the world of mass and the world of pure energy. One of the most astonishing consequences of Einstein's theory of relativity is that time does not flow at the same rate for everyone. If you move quickly enough, especially if you approach the speed of light, your experience of time begins to diverge from that of someone standing still. This phenomenon is called time dilation, and it is not a theoretical curiosity. It is a measurable, experimentally confirmed feature of the universe. The classic illustration is the twin paradox. Imagine two twins. One remains on Earth, the other travels aboard a spaceship that accelerates to a significant fraction of the speed of light. After years of travel, the spacefaring twin returns home younger than the twin who stayed behind. Not because of suspended animation, or biological slowing, or tricks of perception, but because less time actually passed for the traveling twin. Their clocks ticked more slowly. Their heartbeat, their thoughts, their entire timeline unfolded at a reduced pace compared to Earth. This effect is not science fiction. It has been verified repeatedly. Astronauts aboard the International Space Station orbit Earth at about 7.7 kilometers per second. At that speed, their time runs ever so slightly slower than ours. When they return to Earth, they are microseconds younger than they would otherwise have been, the real-world version of the twin paradox, lived by actual humans. GPS satellites offer another dramatic demonstration. Their clocks run faster because they are higher in Earth's gravitational field, a general relativity effect, but also slower because they move at high speed, a special relativity effect. Engineers must correct for both time dilation effects every single day. Without these corrections, GPS systems would drift by kilometers in less than 24 hours. Your phone only tells you where you are because Einstein's equations are built into every satellite. So why does time behave this way? The answer lies in the structure of spacetime. Einstein discovered that the speed of light must remain constant for all observers, in all circumstances. But for that to hold true, something else must change, and the universe chooses to adjust time and distance rather than the speed of light. When an object moves quickly, space in the direction of motion contracts and time stretches, ensuring that the cosmic speed limit is never broken. This leads to a profound insight. It is not light that moves strangely. It is time itself that bends to protect the laws of physics. As an object accelerates toward the speed of light, its timeline begins to tilt relative to stationary observers. Seconds stretch. Processes slow. Clocks tick at different rates. Ultimately, this difference is not optional. It is how the universe preserves causality, consistency, and the fundamental symmetry underlying space-time. In the relativistic cosmos, time is not an absolute river flowing identically for all. It is a flexible dimension, shaped by motion and gravity. It folds, stretches, and adapts, not to accommodate light, but to maintain the deep architecture of reality. As an object accelerates toward the speed of light, not only does its time slow down, space itself changes shape around it. This phenomenon, known as length contraction, is one of the most counterintuitive predictions of special relativity, yet it follows directly from the same geometry that protects the cosmic speed limit. When something moves at relativistic speeds, distances measured along the direction of motion become shorter. In other words, the faster an object moves relative to you, the more it appears to contract along its line of travel. The mathematical heart of this effect is the Lorentz factor, the same gamma that governs time dilation. As velocity increases, gamma grows larger, and the contracted length becomes L equals L a gamma, where L is the object's length at rest. At everyday speeds, gamma is essentially 1, so no contraction is noticeable. But as a spacecraft approaches 90%, 95%, or 99% of the speed of light, gamma increases dramatically, and the contraction becomes undeniable. A starship that is 100 meters long at rest might measure only 10 meters to a stationary observer if it passes by at relativistic velocity. At 99.999% of c, it could appear as thin as a sheet of paper. It is crucial to understand that this is not an optical illusion. It is not a trick of lenses or a distortion caused by light travel time. Length contraction is a real geometric fact, measured within the reference frame of an observer. From the perspective of the stationary observer, the moving object truly occupies less space along its direction of motion. But from the perspective of someone on board the ship, nothing changes. Their rulers, their cabin, the distance between stars remain exactly as they were. Relativity does not distort objects arbitrarily. It changes the relationship between frames of reference in a perfectly consistent way. Why does the universe behave like this? The answer is the same one we encountered with time dilation. The speed of light must be constant for all observers, no matter how fast they are moving. To preserve this universal constant, space and time must adapt. They stretch, compress, and reorganize themselves to ensure that no measurement ever violates the cosmic speed limit. If time slows for fast-moving travelers, then space must contract in the direction of motion so that light retains the same value of c in every frame. Length contraction also has remarkable physical consequences. For travelers moving near the speed of light, the distances between stars shrink dramatically. A journey that appears to be dozens of light years long in the Earth frame might feel like only a few months or years aboard a relativistic spacecraft. The universe itself becomes smaller for those who move quickly enough. In the end, length contraction reveals a profound truth about reality. Space is not rigid. It bends and reshapes itself depending on how you move through it. The geometry of the universe is not fixed. It is dynamic, adaptive, and inseparable from motion. To understand why nothing can exceed the speed of light, we must look not at the particles themselves, but at the architecture of space-time. Einstein showed that space and time are not separate entities. They form a unified four-dimensional fabric in which every event is anchored. And the most important feature of this fabric is the light cone, a geometric structure that defines what is possible and what is forever out of reach. Imagine a single event, a flash of light, a spark, a point in space-time. From that event, a cone-shaped region expands outward, representing all the places that can be reached by signals traveling at the speed of light or slower. This is the future light cone, the domain of all events that can be influenced by the original flash. Likewise, a past light cone gathers everything that could have influenced the event. Together, these cones carve the universe into distinct regions. Or inside the cone, events connected by cause and effect. Or outside the cone, events that can never be reached, no matter how fast something tries to travel. If an object could move faster than light, it would leave the interior of its light cone and enter a region of spacetime that is not causally connected. From the viewpoint of some observers, the object would arrive before it departed. You could send signals to your own past. You could receive messages from events that, in your timeline, have not yet occurred. Physics would permit paradoxes that unravel the very logic of reality. This is the core of causality, the rule that causes must precede their effects. Faster-than-light travel violates this rule not as a technical glitch, but as a structural breakdown. In relativity, different observers may disagree about time intervals or distances, but they always agree on the causal order of events inside a light cone. That order defines what is real, what is possible, and what can unfold in sequence. Remove that order, and the universe ceases to be coherent. The speed of light is not just a maximum velocity, it is the boundary between causally meaningful motion and logical collapse. Every event in the universe has a light cone that constrains the ways information can flow. If something could move outside its cone, information would propagate backward in time for some observers. Entire timelines would contradict themselves. This is why relativity forbids superluminal travel. Not because we lack the technology, not because energy requirements are impractical, but because the geometry of spacetime does not allow it. The speed of light is the steepest slope any signal can climb through spacetime. It defines the shape of every particle's possible trajectory. It protects the chronology of the universe, and it ensures that reality unfolds in a way that is logically consistent. From this perspective, the speed of light is not a speed limit imposed from above. It is the guardian of causality, the rule that prevents the universe from tearing itself apart. Everything that exists, galaxies, atoms, consciousness, the unfolding of time, depends on this boundary holding firm. In Einstein's general theory of relativity, gravity is no longer a force pulling objects through space. Instead, spacetime itself bends, curves, and stretches, and everything, planets, stars, photons, simply follows the geometry laid out before them. Light, in this picture, is not choosing a direction or navigating through a medium. It moves along the straightest possible path in curved spacetime, a trajectory known as a null geodesic. This means the speed of light is not an attribute of photons. It is a property of the metric, the mathematical structure that defines the shape of the universe. The statement "nothing can move faster than light" is therefore not a technological barrier or a physical handicap. It is a geometric truth. It emerges from the way spacetime is stitched together. When space itself curves, light bends. This is why gravitational lensing exists. Massive galaxies and clusters warp the geometry around them, and light traveling through that region follows the curvature, creating arcs, rings, and distorted images of distant galaxies. The photons never change speed. They simply move through a landscape that is not flat. This curvature becomes extreme near black holes. At the event horizon, the geometry of spacetime tilts so steeply inward that even light cannot escape. Nothing is held back by a force. Rather, every possible path that light could take leads deeper into the black hole. The horizon marks a shift in geometry, not a wall or physical barrier. Inside, the metric changes so drastically that all future directed paths converge toward the singularity. General relativity also explains a subtle but often misunderstood phenomenon. Space can expand faster than light. Galaxies at the edge of the observable universe recede from us faster than c, not because they are moving through space at superluminal speed, but because space itself is stretching. Relativity places a limit on velocities within space, not on the expansion of spacetime as a whole. No object locally outruns light. Instead, the fabric of the cosmos carries distant galaxies away faster than any signal can bridge the gap. This distinction clarifies the true role of light speed. It is not a limit imposed on technology or engineering, but a structural feature of the universe's metric. Every measurement of distance, duration, velocity, and gravitational influence is encoded in the geometry of spacetime, and the number c appears inside the metric as a fundamental constant, the conversion factor between space and time. It determines the shape of the light cone, the curvature of geodesics, and the structure of causality. In a curved universe, nothing can exceed the speed of light for the same reason nothing can step outside its own shadow. The limit is built into the definition of motion itself. It is a feature of the geometry we inhabit, not a frontier we can engineer our way past. Thus, the impossibility of surpassing c is not a failure of technology. It is an expression of the deep architecture of reality, a sign that the universe itself is written in the language of geometry. Whenever scientists declare a limit in physics, human imagination immediately looks for loopholes. If nothing with mass can reach the speed of light, then what about particles that start off faster? What about quantum tricks? What about bending space itself? These possibilities are fascinating, but each ultimately reinforces, not contradicts, the fundamental speed limit of reality. One theoretical idea is the tachyon, a hypothetical particle that would always move faster than light. Tachyons arise naturally in certain mathematical solutions to relativistic equations, but they have a fatal flaw. If tachyons existed, they would allow information to be sent backwards in time for some observers, collapsing causality and producing paradoxes that break the logical structure of spacetime. Their presence would destabilize every known quantum field theory, making the vacuum itself unstable. Because of this, physicists believe tachyons do not exist physically. They are mathematical ghosts, a signpost that the equations allow bizarre solutions, not evidence of any real faster-than-light particles. Quantum tunneling offers another tempting hint. In tunneling, a particle appears on the other side of a barrier faster than it would take to cross it classically. To many, this looks like superluminal travel. But the truth is more subtle. No information travels faster than light during tunneling. What propagates is a probability wave, not a signal. The apparent speed is a feature of how quantum amplitudes evolve, not a violation of relativity. Quantum mechanics preserves causality perfectly. Then there are the exotic concepts from general relativity, warp bubbles, wormholes, and shortcuts through curved spacetime. These ideas are not about moving faster than light through space. They are about rearranging space around you. A warp bubble compresses space in front of a ship and expands it behind, allowing the ship to ride inside a pocket of flat space while spacetime itself flows. A wormhole connects two distant regions of the universe through a higher dimensional tunnel. Both scenarios seem to allow arriving somewhere faster than light could travel through normal space. But both require something nature has never provided: negative energy or exotic matter. Negative energy is permitted in quantum theory in tiny, fleeting amounts, but sustaining a macroscopic region of negative energy, large enough to stabilize a wormhole or power a warp bubble, appears to be impossible. Even if it were possible, these geometries do not break relativity's rules. They do not allow an object to exceed c within its local frame. Instead, they exploit the flexibility of geometry. The speed limit remains intact. Spacetime simply folds around the traveler in such a way that the journey appears superluminal from the outside. In other words, all attempts at exceptions reinforce the same lesson. Nothing can outrun light in normal space. Quantum tunneling does not transmit information faster than c. Warp bubbles and wormholes do not exceed the limit. They circumvent it by reshaping the metric. Relativity is not fragile. It is astonishingly robust. Its speed limit is not a fence to be climbed over, but a fundamental feature of the terrain, the geometry of the universe itself. The speed of light is often misunderstood as a limit on how fast particles can move, as though nature simply refuses to let objects become too quick. But this perspective misses the deeper truth. Light speed, the constant c, is not a speed chosen by particles. It is a property of spacetime itself, a boundary written into the geometry of the universe long before stars, photons, or atoms existed. In relativity, c emerges as the maximum rate at which cause can influence effect. It defines the steepest possible slope of any trajectory through spacetime. No signal, no force, no interaction can get ahead of light, because doing so would break the causal structure on which the entire universe depends. This is why physicists say that the speed of light is not simply a velocity, it is the speed of information. If information could move faster than c, clocks would disagree not only about durations but about the sequence of events themselves. For some observers, the effect would precede the cause. Messages could be sent into the past. Paradoxes would proliferate. The timeline of the universe would lose coherence. Without a causal boundary, physics would not simply be strange, it would be logically inconsistent. Seen this way, the limit c is not a restriction imposed on us. It is a stability condition for the universe. It protects chronology, enforces consistency, and ensures that the laws of physics behave identically for all observers. Remove this boundary, and the equations of relativity collapse. Quantum field theory ceases to make sense. Even the idea of motion becomes undefined. The constancy of c also anchors the unification of space and time. It tells us how distances translate into durations, how energy becomes mass, how gravity affects clocks, and how particles propagate through the vacuum. Every field, every interaction, every fundamental equation carries the imprint of this single constant. If you changed C, even slightly, the entire structure of reality, atoms, stars, chemistry, life, would unravel. Thus the speed of light is not a limit to be surpassed. It is the foundation on which the universe is built. The cosmic speed limit is the reason reality behaves coherently. It is the rule that makes communication possible, that protects cause and effect, and that allows the universe to unfold in a stable, predictable way. In this sense, c is not the maximum speed of motion. It is the deepest organizing principle of existence. In the end, the universe is not governed by chaos, but by structure. It does not allow events to unfold in wild disorder, nor does it permit signals to wander freely through time. Instead, it holds itself together through a single, elegant constraint, the speed of light. This limit is not a wall we crash against. It is the quiet boundary that shapes every process, every chronology, every possibility that unfolds within space-time. The cosmic speed limit is not about how fast something can move. It is about what the universe allows to happen at all. It binds cause to effect, ensures that messages cannot outrun their origins, and prevents timelines from twisting into paradox. Without this boundary, the laws of physics would lose their coherence, information would flow unpredictably, and the very notion of before and after would dissolve. Seen in this light, C is not an obstacle, it is the foundation of order. It is the constant that unites space with time, energy with mass, gravity with geometry. It is the thread from which the tapestry of reality is woven. And so we end with a poetic truth. The speed of light is not about motion. It is the boundary that allows the universe to be itself. It is the rhythm that keeps causality intact, the measure that preserves meaning, and the invisible architecture that holds together every moment we experience. The universe is not limited by C, it is defined by it. And within that definition, everything we know, from the orbits of planets to the beating of hearts, finds its place in the cosmic order.